Okay, hello there. I wanted to go through a presentation, a practice presentation on representations of the special linear 2C Lie algebra. So what we will first consider is the vector space base Vm consisting of polynomials in two complex variables that are homogeneous. Did I spell that right? EOUS, yeah, my bad. That are homogeneous. Then we will define a Lie group representation from SU2 to the general linear group on Vm. And this will take, in the representation, pi, capital Pi m. The representation will act on polynomials f and take them to polynomials composed with the inverse of u. Now, of course, these polynomials will look like the following. Right, z1, z2 for the two complex variables. Maybe I want to write it the other way. Now I'm totally twisted around here. So we have a homogeneous polynomial. There are, in its general form, there are 1, 2, m terms counting in the exponent of the z2 variable, and then m plus 1, where the z2's zeroth the zeroth entry for the z2 variable is the m plus 1th dimension. Okay, so we will briefly show that pi m is in fact a Lie group homomorphism. Clearly smooth, but to show that it has the algebraic properties. Through direct computation, we see that we still have a a homogeneous polynomial. So it is in fact acting on Vm. And now to show that it respects the group action, U2 and U1 are both special unitary matrices. So then this equals F composed with the inverse of U2 composed with the inverse of U1. And that equals nothing more than F of inverse U2 times the inverse of U1 composed with Z, and then through basic linear algebra, you can rewrite it thusly. And we see that the multiplication operation is respected. Okay, excellent. So now we have developed this representation of SU2 acting on VM. So because of how nice matrix Lie groups are, we'll be able to directly compute the Lie algebra homomorphism induced by this Lie group homomorphism. So remember, the Lie algebra, or that I'm going to call the Lie algebra homomorphism that I'm going to call lowercase pi m of x, let's say, acting on f of z is equal to the derivative of the homomorphism of the exponential evaluated at 0. And since pi m, capital pi M, has been specifically identified, we can explicitly compute this. Of z at the identity. Okay, good. So an important step to remember here is, well, we're going to want to apply the chain rule, but what is the function that we're composing with? E to the negative xt times z, which can be viewed as a path in the space of this two-dimensional complex vector space. And then, so that's good because it's particularly easy to take the derivative of paths. And on top of that, the matrix exponential also has a familiar derivative, because it's basically just the regular exponential's derivative. It's always nice when those properties line up. Okay, anyway, so pi, lowercase pi of m, x, lowercase pi m of x is equal to df dz1 times dz1 dt plus df dz2 times dz2 dt. And what are dz1 dt and dz2 dt? Well, we computed them over here. So when you plug that in, we get negative x11, the entry of x. Maybe I'll just put the minus in front. Plus x12 z2 plus z df dz Actually, again, I'll just move the minus out in front. 2, 1, Z1. And there we go. We have a explicit computation for how every representation of a particular matrix X in the space of special unitary matrices, or I guess the Lie algebra of special unitary matrices, will look like. Okay, so now let's take a step back and discuss what the goal was and how this relates to it. So we started out talking about the special linear Lie algebra. But what we've developed is have is pi m a Lie algebra homomorphism for the special unitary group in 2 dimensions. So how is this going to help us get to SL2C? Well, the complexification of SU2 is actually homeomorphic to SL2, and I guess, yeah, in some sense it just is SL2C, because every special linear, every matrix in the special linear Lie algebra admits a decomposition into 2 components that I think look something like this. And in particular, each of these components are in the SU group. So its complexification is homomorphic to SL2C. And so, therefore, pi m might be defined on SU2, but it admits an extension to SL2C, its complexification. So we will now go about defining, or not defining, from this computation we did over here, we can find what every representation is going to look like of any particular matrix in SL. So what we're going to want to do from that is look at some of the basis vectors for SL2C. Zero 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 one zero zero 0001. Actually, it should be in the other corner. My bad. 0010, and then H1001. And this makes sense because remember, SL2C equals trace the matrices with trace equal to 0. Right. So that's why that should be a -1 in that corner. Or you could put the negative on the other one, it doesn't matter. But remember, we just need the diagonal components to cancel out. Okay, good. So now we can use this formula to calculate what these representations are going to look like. So we'll see the basis of the Lie algebra acting on the basis of the vector space Vm. And these are direct computations. I won't show them here because they're easy enough to do, maybe with just one remark that I'll give after I'm done writing. Okay. And y takes that basis vector and it moves z1 up 1, moves z2 down 1. And just really quickly, the way you want to apply the formula we came up with here is, remember that the partials here are not basis vectors in the tangent space, but they are actually derivatives. So you'll actually apply the derivative to the monomial z1 m minus k times z2 k. Then we won't use h soon, but we might need it later, so I'll just write it down. 2. Okay. Equals k z1 shoot, my notes are a little bit backwards here. Equals minus k z minus k z2 and so basically what this is saying is x moves z2 up, y moves z1 up, and h, every representation of h is going to have the basis vectors as an eigenvalue. Okay, let me double check that real quick because I think I might have gotten the eigenvalue for h screwed up. So I think it should actually be, so it should be negative m plus k, actually minus k, it's k, plus k, and then all of this times z1 mk times z2 k. And then that, of course, simplifies to 2k minus m. z1 mk, z2 k. Okay, good. Increase z. Okay. So with that out of the way, we'll just make one statement about this. So there is at least one representation for each dimension and it is pi, capital Pi m, and lowercase pi m. Now let's show that it's irreducible. Lowercase, that is, pi m is irreducible. Let W be a subset of Vm that is invariant under little pi m and is not 0. We will show that W actually equals Vm. Okay. So let P be a member of W and let it have the form Z1m plus A1 Z minus 1 Z1 2 1 to A K Z, maybe I'll use N Z1 M minus N Z2 to the nth power. N is free to be equal to or less than M, where N is equal to or less than M. So basically saying in this subspace there is some polynomial of largest degree with respect to Z2. And then through repeated applications of, I believe, pi x, repeated applications of pi x, we can go all the way up. We'll go all the way up this chain. Then n times of pi of x. I'll put the n there. So this just means n repeated applications of pi mx onto p will give us some constant multiple of z wait, is that the direction I want to go? Which direction are we going? So we found the lowest. Okay, I guess I actually want to so we want to get to that point x takes us to yes. So decreases Z1. So we want to decrease Z1 until we're only left with Z2, some constant multiple of Z2, to the M, and then because some constant multiple of Z2 to the M is in W, because we said this was an invariant subspace, we then have just the basis vector, the monic basis vector z2 to the m, also in the subspace. And then with repeated applications of y to the little m power on z2 to the m, that will cause z2 to go down, and we'll be left with some constant multiple of z1 to the m. So there we go. We went all the way to the top of greatest degree with respect to z2, and then we went through every intermediate basis vector. So we now see that z1 m minus k times z2 to the k is in W for all k greater than or equal to 0 and greater than or equal to m. In other words, W is equal to Vm, so pi m is irreducible.